Welcome to a session on conductivity of electrolytes. Just like metallic conductors, electrolytic solutions also conduct electricity. And similar to metallic conductors, these solutions also offer resistance to the passage of current. You all know that resistance R is measured in ohms and it is directly proportional to the length of the conductor and inversely proportional to the area of cross section of the conductor. To remove the proportionality sign and to introduce an equality sign, we have to introduce a proportionality constant. R is equal to rho, that is the proportionality constant here, rho into L by A. R is resistance, rho is the proportionality constant and it is called here resistivity. L is the length of the conductor, area A is the area of cross section of the conductor. Now I can rewrite this equation as rho is equal to R into A by L. Resistivity is equal to resistance into A by L. If we have to define it in words, we can say when A is 1 square centimeter or square meter and L is 1 centimeter or 1 meter. When A and L are unity, rho is equal to R. Isn't it so? So we can define resistivity. Resistivity is the resistance of a conductor of unit length and unit area of cross section, or we can say it is the resistance of a cubic centimeter of a conductor, or it is a cubic meter, 1 cubic meter of a conductor. Let us determine the unit of rho. Unit of rho, you can write it yourself. Unit of rho is ohm and centimeter, ohm centimeter, or it can be ohm meter, ohm centimeter or ohm meter. What is the relationship between these two? Let us see. 1 ohm meter we can write is equal to ohm into 100 centimeter. So that will be equal to 100 ohm centimeter. Reciprocal of resistance 1 by R. This is called conductance. 1 by R is conductance. And it is given as symbol G. The unit would be 1 by ohm. So we say ohm inverse or ohm to the power minus 1. This is also called mho, or it is given the unit Siemens. Now let us consider the reciprocal of resistivity 1 by rho. 1 by rho is called conductivity. Conductivity, which is given a symbol kappa. Now let us see how in what units we can express kappa. Rho is equal to R into L by A, and 1 by rho is kappa. Kappa is equal to 1 by rho, which is equal to 1 by R into L by A. 1 by R, so unit should be ohm inverse because it is in the denominator, into, here it is length by length squared, so it can be ohm centimeter inverse or ohm inverse centimeter inverse or ohm inverse meter inverse. Kappa can be expressed in 2 units, ohm inverse centimeter inverse or ohm inverse, meter inverse. Let us see the relationship between the two. 1 ohm inverse ohm inverse meter inverse can be written as ohm inverse by meter. So that is equal to writing ohm inverse by 100 centimeter. So I can write it as ohm inverse centimeter inverse by 100. So I can say 100 ohm inverse meter inverse is equal to 1 ohm inverse centimeter inverse, centimeter to the power minus 1. So this is the relationship between the two, because often we are given A and L in terms of meter squared by meter or centimeter squared by centimeter. So we have to be familiar with the interconversion. For practical purposes we will be using centimeter, but meter being the SI unit, you can often get problems in these units also. So it is better to know the relationship between the two units. We have learnt a few terms with regard to conductivity of conductivity by metallic conductors, or particularly we are going to consider conductivity of electrolytic conductors. So I am going to enter all these terms that we have learnt in terms of a tablet. Let me enter the quantity that is measured in the first column. Quantity measured. In the second column you can write symbol. Third column we will write down the unit. So first let us write resistance. That is the first quantity of any conductor. Symbol is R, unit is ohm. Next, resistivity. Resistivity, or it's also called specific resistance. Specific resistance. Symbol is rho and it is ohm. Ohm meter or ohm centimeter. This ohm is also expressed as by this expressed in this form. Conductance is the third one. Conductance G, and the unit is ohm to the power minus 1 or mho or Siemens. The fourth one is conductivity or specific conductance. Kappa, and the unit is ohm inverse centimeter inverse or ohm inverse meter inverse. Very often it is given as Siemens centimeter inverse or Siemens meter inverse. This is the way we will be expressing the conductivity of electrolytes. So we have entered all the terms that we have learnt with regard to electrolytic conductance and their units in this tabular column. The next thing to be considered is the difference between metallic conductors and electrolytic conductors. Let us write metallic conductors in one column and electrolytic conductors, that is electrolytes, solutions of electrolytes. The first thing is metallic conductors or conduction by metals involves movement of electrons. It involves passage or movement of electrons. In the case of electrolytes, the electricity is conducted by the passage of ions. It involves movement of ions. Secondly, you know the resistance of a metallic conductor decreases with increasing temperature, or rather resistance I would put it this way, resistance increases with increasing temperature. We know that as the temperature is lowered, the resistance offered by metals decreases. That is why we have superconductors at very low temperatures. But in the case of the electrolytes, conductivity increases. Conductivity increases with increase in temperature. Here I said resistance increases with increasing temperature. So when resistance increases, conductivity decreases. It is just the opposite. So we can also write resistance increases with increasing temperature, or conductivity decreases. Conductivity decreases. Here conductivity increases with increase in temperature, because in electrolytes the conductivity is by the movement of ions, and we know that by increasing the temperature, the kinetic energy of the ions will increase, so the velocity also will increase, hence the conductivity will be more. Third one, there is no change in the material. When it is conducting electricity, there is no change in the material of the metallic conductor. Whereas here the chemical composition may vary, because the electrolytes may get deposited at the electrodes, the ions may get deposited at the electrodes, so the chemical composition may vary. The chemical composition may vary. The concentration could change, and so it definitely brings about a change in the electrolyte. So these are the three major differences between metallic conductors and electrolyte. Now that you know that ions are the carriers of current in an electrolyte, it shouldn't be difficult for you to mention the factors on which conductivity of an electrolyte depends. Let's list them out. 1. Number of ions. Larger the number of ions, higher will be the conductivity of an electrolyte. For this we can also write concentration of solution. Secondly, we can say temperature. When the temperature is higher, ions have greater kinetic energy or velocity, and hence they can conduct better. So temperature is an important factor. Third, nature of the electrolyte. You know, weak acids do not dissociate completely at all concentration, weak acids and weak bases, and so they may be providing less number of ions. Fourth, we can say size of ions. Larger ions move slowly, hence conductivity is less for larger ions. Fifth is nature of the medium or viscosity of the nature of solvent or viscosity of medium, we can say. So that is giving you the list of the factors on which conductivity of an electrolyte depends. The next thing would be to determine the conductivity of the given electrolyte. Since the conductivity of an electrolyte depends on concentration, we have to prepare solutions of known concentration to measure the conductivity. So first thing, we prepare a solution of known concentration, and you know kappa is equal to cell constant by resistance. If we know the cell constant of the cell in which we take the solution and measure the resistance of the solution, we can calculate conductivity. For determination of resistance for the electrolytes, we take them in conductivity cells. One of the conductivity cells could be of this shape. This is the tube like thing in which two electrodes are fused. You can take the conductivity, you can take the solution whose conductivity is to be determined in this conductivity cell. You can also have something like this. It could be a beaker with a lid to which two electrodes are fixed. You can take the electrolyte in this container also and determine the conductivity. First thing is we have to determine the resistance. For that, we place this conductivity cell carrying the electrolyte in the place of the unknown resistance in the Wheatstone bridge. And I don't have to explain the details. You can determine R by the Wheatstone bridge experiment for the solution which is taken in this conductivity cell and placed in the place of the unknown resistance. For cell constant, we use solutions of KCl of different concentrations for which the conductivity values are determined and listed. So, for KCl solution, you can say it is almost a standard solution in this regard. For KCl solutions of different concentrations at different temperatures, the conductivities are measured and listed. So, we can take KCl solution of a certain concentration in this conductivity cell and determine its resistance, as I explained just now. We can take the value of kappa from the list. We have measured R for KCl. We can take the value of kappa from the given data, and so we can calculate cell constant, which is a product of these two. Once you know the cell constant of this conductivity cell and that we have measured R, it becomes very easy for us to calculate conductivity. Is that clear to you? So, using a solution of KCl of known concentration, we determine the cell constant of the conductivity cell. This is what you have to know here. And resistance you can measure. And once these two data are available, we can calculate conductivity of any electrolyte of any given concentration. We will do a simple problem based on the formula. In this problem, you are given the conductivity of a solution of sodium chloride and also its resistance. You are required to calculate the cell constant. It's a simple substitution problem. You can you have the necessary data there, so you can substitute and work out and get the result. I believe you have worked out the problem. Now you can refer to the solution and check your answer. Since conductivities of solutions depend on concentration, to compare different electrolytes in the same solvent at the same temperature, we need to have a common concentration base. For that purpose, we use molar conductivity. Molar conductivity can be defined as the conductivity of all the ions present in a solution containing 1 mole of the electrolyte placed between two electrodes. It can be represented as lambda m is equal to kappa by C, where kappa is the conductivity of the solution and C is the concentration of the solution. C can be expressed in mole per meter cube or mole per centimeter cube. Now when kappa is in Siemens centimeter inverse and concentration is C mole per meter cube. So that meter cube can go up, meter cube we get an expression like this. And so the unit for lambda m or molar conductivity when we use these units would be Siemens meter square mole to the power minus 1. So lambda m is equal to K by C Siemens meter square mole to the power minus 1. When K is expressed in Siemens centimeter inverse and concentration is given as C mole per liter, let us see how we have to do it. Now for liter we have to write 1000 centimeter cube so that we get the same unit everywhere. By C mole. So the unit would be K by C, the unit would be Siemens centimeter square mole inverse, but remember there is a 1000 here. There is a 1000 here, that is very important. I will rewrite that here once again. Lambda m is equal to K into 1000 by C Siemens centimeter square mole to the power minus 1. You can have problems in any of these units. Look at the unit, and if it is the centimeter unit, remember to use 1000 in the formula. Only then you will be correct. So that is a very common mistake that the students make. So if meter unit is used, you can simply use the formula lambda m is equal to K by C. But when centimeter unit is used, you have to make sure that you have 1000 in the formula. It will be K into 1000 by C. Now let us see the relationship between the two units. 1 Siemens meter square mole to the power minus 1 will be equal to Siemens per meter square. I will substitute 100 centimeter the whole square mole to the power minus 1. So you get 10 to the power 4 Siemens centimeter square mole inverse. Whenever necessary, you can easily derive it this way. So we have learnt two important formulae here for molar conductivity. Molar conductivity is equal to K by C Siemens meter square mole to the power minus 1, or molar conductivity lambda m is equal to kappa into 1000 by C Siemens centimeter square mole to the power minus 1. We will work out a few problems on molar conductivity. To begin with, read the given problem. As I always say, pause here, work out the problem, and then refer to the solution. For the solution, let me write down the given values with the units. Concentration of the solution. That is 0.01 molar. Resistance has a value of 200 ohm. Cell constant is given as 0.88 centimeter to the power minus 1. We are required to calculate the conductivity and molar conductivity of the solution. Conductivity kappa is given by cell constant by resistance. So we will substitute the values here. 0.88 centimeter to the power minus 1 by 200 ohm. So that gives you a value of 4.4 into 10 to the power minus 3. This will be ohm inverse, centimeter inverse, or we can say Siemens centimeter to the power minus 1. molar conductivity lambda m is equal to kappa by C, concentration in mole per liter. Here we have to remember to include a 1000 in the numerator because this is mole per liter. Liter is 1000 centimeter cube and kappa is given in centimeter to the power minus 1. So we have to be very careful here. This is a place where very commonly the students are making mistake. They just substitute K and C as 0.01, whatever concentration is given, but they forget to include 1000 for a liter here, 1000 centimeter cube for a liter. Now let me write the value of K, 4.4 into 10 to the power minus 3 into 1000 by concentration 0.01. So this is Siemens 10 centimeter to the power minus 1, this is centimeter cube. So while writing the units, we will write the value comes as 440 Siemens centimeter square mole inverse. Let us do one more problem. This is the second problem. A solution of an organic acid of concentration 0.200 mole decimeter to the power minus 3 has a conductivity of 0.184 ohm inverse meter inverse at 25 degree Celsius. Calculate its conductivity and molar conductivity. So you are given here concentration and conductivity, and you are required to calculate molar conductivity. You are required to calculate only the conductivity, not its. You have to calculate only the molar conductivity. This is a very simple, straightforward problem of substitution and calculation. But there is something that requires your attention here. We have to be very careful about the units. I will show you while doing the problem. So let me write concentration of the solution, which is 0.200 mole dm to the power minus 3, that is mole per decimeter cube. It is same as mole per liter, and conductivity is 0.184 ohm inverse meter inverse. See here, this is given in meter unit and this is given in liter or decimeter unit. So we have to bring them to the same unit. That is the thing that needs attention here. Otherwise it is a simple problem. Lambda m is equal to kappa by C. For kappa, let us substitute the value 184 ohm inverse meter inverse by concentration 0.200 mole dm to the power minus 3. When we take it to the numerator, that will become decimeter cube. So I will rewrite it as 184 ohm inverse meter inverse by 0.200 mole. This is decimeter cube. Now for this, I can write it as 10 to the power minus 1 meter the whole cube, isn't it? When I do that, the answer comes at, I will write the answer here, 9.2 into 10 to the power minus 4 ohm inverse. This is meter to the power minus 1 meter cube. So meter square mole to the power minus 1. Okay. Let us do one more problem before concluding the session. This is the last problem of the session. it's a pretty long problem, but doing this problem will make you familiar with all the relationships between the various terms that you learnt in connection with conductivities of solutions. I expect you to do the problem. Anyway, the solution follows. Here in this problem, you are given the resistance of 0.01 molar KCl solution. So let us write that. Resistance of 0.01 molar KCl, that is 797 ohm. You are also given resistance of 0.01 molar AgNO3 solution as 901 ohm. So it becomes clear to us that the resistance of the KCl solution is given mainly for calculation of the cell constant, because all that we require for the solution is about for the solution of AgNO3. All the other values that we require are for AgNO3 solution. So we need to calculate cell constant. For the purpose of that only, the resistance of 0.01 molar KCl solution is given. So we also need to know the conductivity of this solution. We already discussed that so KCl solutions of various concentrations, conductivities are determined and listed. So from the list the value is given. So we will use the resistance and the conductivity value of KCl to calculate cell constant. You know, kappa is cell constant by resistance, so we can say cell constant is equal to kappa of KCl into R of KCl, that is 0.1427 Siemens meter to the power minus 1 into the resistance 797 ohm. That gives you a value of 112 meter to the power minus 1. Why? Because Siemens is ohm to the power minus 1, this is ohm, so those two cancel, you get meter to the power minus 1. Next thing that we have to calculate is the conductance G of AgNO3 solution. Conductance G is equal to 1 by R, 1 by resistance. What is the resistance? We are given a value of 901 ohm for AgNO3 solution. So that gives us a value of 0.0011 ohm to the power minus 1. That is the conductance. The next thing that we have to calculate is kappa. For kappa of AgNO3, we need the cell constant, which we have already determined as 112 meter to the power minus 1 by resistance 901 ohm. This gives us a value of 0.125 ohm to the power minus 1 meter to the power minus 1. Next thing is rho, which is resistivity. Resistivity is the reciprocal of conductivity. So resistivity is equal to 1 by K. Kappa value we just now got it as 0.125 ohm to the power minus 1 meter to the power minus 1. So this gives us a value of 8.01 ohm meter. Last thing to be calculated is lambda m, molar conductivity, which is given by conductivity by concentration. Here, because everything is in meter unit, we have to take the concentration in mole per meter cube. First, let us first write the conductivity value, which is 0.125. For ohm inverse, I will write Siemens meter to the power minus 1. I am using different units so that you are get familiarity with everything. Meter to the power minus 1 by concentration. Concentration of the solution is 0.01 mole per liter. So that liter goes up. I will write the liter here. And I am going to substitute for the liter (0.01 mole) 10 to the power minus 3 meter cube. Already we have seen that. For decimeter cube in the previous problem we worked out 1 decimeter cube is 10 to the power minus 3 meter cube. So here I am straight away writing, because decimeter cube and liter are the same, I am writing 10 to the power minus 3 meter cube. That gives us a value of 0.0125 Siemens I suppose I am right here, 0.0125 Siemens meter square mole to the power minus 1. I suppose you have learnt the various concepts that we discussed in this session. Thank you.